Welcome to Lecture 4. In this lecture, we're going to deal with the same general area of natural science that we dealt with in the last lecture, but there's going to be a difference, a big difference, in the way the subject is dealt with today from what we did last time. There, recall, we examined attempts by natural philosophers, primarily in the 18th century, to explain how the earth and its creatures came to have the features they do through an appeal to causal natural laws. They took their cue from astronomy, which in the 17th century had seen so many discoveries of the natural laws that ruled the motions of the heavens. All that culminated, of course, in the work of Isaac Newton, whose own reputation soared as the 18th century proceeded. We saw last time how the discovery of new natural laws led to the practice of replacing God's direct action as the explanation of why nature was as it was, with the natural law itself as the explanation. That is, natural philosophers placed the operation of natural laws God had imposed as the direct cause. Where the mountains or the motions of the heavens were concerned, that just made the truths of the Bible more reasonable for many. But others were less concerned with what the Bible said and began to allow their systems to become quite elaborate. We examined how de Molay concluded that there had been a long-acting evolutionary process of development of the earth and of life. It was brought about as the result of the gradual diminishing of the primal waters that, he said, originally covered the earth. We followed Buffon as he appealed to an extended natural process of the cooling of a piece of the sun. The earth's features developed as they did, and life appeared and developed because of this gradual cooling. Finally, we saw how Hutton focused on the earth's interior heat as the causal agency that drove what for him was an indefinitely long cycle of decay and renovation. What all three theories of the earth had in common was an appeal to a causal agency, the gradual diminishing level of water, the slow cooling of molten mass, or the constant pressure from the interior heat of the earth. All these to explain why the earth is as we see it to be. Theories of the earth were causal explanations of the earth's features. Of course, they also had in common that the various causal processes each took a long, long time, much longer than the age of the earth most people in the 18th century were used to. I emphasized that these theories of the earth were what we've called deistic, and that deists were not atheists. God was necessary as the creator of the laws. God operated on nature, but not directly by fiat. God operated by remote control through the laws. Today, I want to consider another 18th century approach to understanding the earth and its history. Its most distinguishing feature, and this marks it off from the theories of the earth we examined in the last lecture, was its reluctance to search for grandiose and universal causal laws to explain the present features of the earth's surface. The approach was given a name by its most celebrated proponent, but the name won't mean much to you since it's a term that did not last in the history of science. Don't worry, I'm going to give you the name in just a minute. For right now, let me just say that the approach emerged on the continent in Germany. It came out of the German mineralogical tradition. This was an old tradition in Germany. Some of the German states were blessed with rich deposits of ore. So naturally, there was a lot of attention given to metals and mining. In regions like the Erz Mountains of Saxony, for example, there had grown up a mining tradition that by the 18th century was long established, and mining officials were always looking for practical information about the location and properties of valuable metals like lead, copper, and silver. Now, in the 18th century, German states began establishing technical schools, separate from the universities, for the purpose of training the officials they required. As these technical schools grew and their curricula developed, the German approach to mineralogy expanded beyond its primary interest in metals. We might expect that in such an academic context, the German mineralogists would begin to entertain grandiose theories of the earth, as we saw happen in France and in Scotland. But they didn't. These German scholars appeared not to be interested in searching for universal causal laws. They were, in fact, much more empirically oriented than interested in theory. They far preferred to gather information about the various forms of solid materials found on the Earth. Their focus stayed on the Earth and its features. They were not as much interested, for example, in the development of life as were the theorists of the Earth. From what I've said about them, you might think they were only interested in practical knowledge. Well, they were practical, of course, but it wasn't always clear that the empirical information they gathered, as we'll see shortly, was going to yield practical benefits. And it's not as if they never used their data to make inferences about the Earth's past either. They did. It's just that their approach was not to go out seeking universal causal laws about the history of the Earth. To the extent they had ideas about the Earth's history, they came as implications from their classification of a wealth of empirical information. I want to emphasize that this German mineralogical tradition is both interesting in its own right, and it's also really important for later developments. I say this because many in the early 19th century, especially on the continent, liked to identify with the empiricism of this tradition. Not only so, they associated themselves with it in order to dissociate themselves from the more speculative traditions of the theorists of the Earth. In addition, some key notions in later geology came from this tradition. I'm thinking here of the importance of rocks, and even the idea of a rock formation. So let's turn our attention to what's in this tradition. By far, the central figure in this 18th century story is Abraham Werner. Werner was born in Silesia, but he studied and taught later at the mining academy in Freiberg in Saxony. He's something of a mysterious figure since we don't have a lot of information on him. He published a little during the last quarter of the 18th century and some after the turn of the new century, but not much. What we know of him and of his system comes from the little he did publish, from what scholars have found in unpublished materials, and from the students who flocked to Freiberg to hear him. That's where his reputation was made as a teacher. I've done a lot of my own research in the early German Romantic period, and I can tell you that if you were young and at all interested in natural science at the end of the 18th century and the beginning of the 19th century, one of the places you just had to go was to Freiberg to hear Werner for a while. The great German writer Johann von Goethe, who began his climb to fame in the mid-1770s, was a convinced Wernerian and remained so his entire life. Now, Werner did not spring up out of nowhere. He was deeply indebted to that old German mineralogical tradition I mentioned a moment ago. So we need first to learn what Werner inherited from his predecessors. Once we've done that, we'll examine what he contributed that earned for him the international reputation he acquired. By the 18th century, there had grown up many different ways of classifying what were known as minerals. One common classification scheme included 4 classes. First, there were what were called earths. This is the solid matter of soils, but it also included rocks. The second class was metals. I mentioned metals above. Materials like copper, lead, gold. These had obvious uses, and therefore it's not surprising they constituted a class by themselves. Third, there were salts. Salts were dry, solid materials that resulted from interaction with acids. Sometimes they were soluble in water, sometimes they were resistant to fire. The fourth and last class of minerals was the sulfurs. We might call them hydrocarbons. Here there were substances that burned, like coal and bitumen. As I mentioned earlier, German mineralogists had a tradition of gathering empirical information about these various forms of solid materials found on Earth. We're interested here primarily in the first class of minerals, the earths. We'll look at the metals and sulfurs when we come to the story of the chemical revolution of the 18th century in lectures 5 and 6. Earths, remember, were made of the solid matter of soils, and they included rocks. Let's divide the earths then into rocks and non-rocks. There were two different ways the German mineralogists analyzed earths, and it tended to depend on whether you were talking about rocks or other earths. For earths other than rocks, mineralogists preferred an analysis called the wet way. That is, what you'd do is put the earth into water and test it for solubility. You knew the hot springs at health spas contained dissolved earths because sometimes you could get them to precipitate out. Not surprisingly, the German mineralogists had also developed an interest in chemistry. They read what they could and interacted with chemists when possible to learn what chemistry taught about interactions of earths with acids and bases. In these ways, the German experimenters had, by the time Werner came along, differentiated a whole range of earths based on their solubility. So much for the earths that were not rocks. Another aspect of the mineralogical tradition Werner inherited had to do with earths that were rocks. Now, prior to the 18th century, rocks, for the most part, were regarded as mere conglomerations of individual minerals. As such, they weren't particularly interesting, not worthy of study in their own right. In the 18th century, German scholars began to take a different attitude. They began to subject rocks to classification. To do this, they used what became known as the dry way. That is, they subjected rocks to heat and categorized them according to the effect that heat had on them. The purest rocks were those whose mineral content remained unaltered by even intense heat. Finally, they began to gather more information than just the mineral content of the rocks. I mentioned that they gathered all kinds of empirical data. Well, here's a good example of what I meant. They recorded, for example, such things as the elevation where the rocks were found. They noted and recorded any fossil content. They indicated if rocks were slanted or flat. And they also listed impressions about how old they thought the rocks might be, and even how the rocks might have originated. This latter conjecture strikes me as coming from mostly a purely academic interest, more than a practical orientation. So there had grown up a certain interest in the history of the Earth, even if it was not of the type we saw in the theories of the Earth we've investigated in the last lecture. In this German tradition, there was widespread agreement among 18th century mineralogists that the ocean itself, referred in the biblical book of Genesis, had been a thick gelatinous aqueous fluid. They assumed it must have been made up of minerals in solution. Here's where the German tradition went its own way. The German mineralogists thought that rocks and most other solid materials had formed over time by a process of consolidation of the minerals that were originally in solution. The thick gelatinous fluid that covered the primal earth was like that because all the minerals that were dissolved in it. Over time, these minerals somehow consolidated. I suppose they somehow precipitated out of that original fluid. Now, this is not a particularly easy process to visualize, and it wasn't all that clear to the Germans either. A noted contemporary historian of this German mineralogical tradition has said that consolidation, what she calls the transition from fluidity to solidity, was so central to German mineralogy that it constituted not only a major problem, but likely the major problem to be tackled until the end of the 18th century. This, then, was the background to the work of Abraham Werner. It would be Werner who drew upon the collected wisdom of his predecessors to create a geological system that made him famous all over Europe in the late 18th century and after. He was the one who put it together and gave it distinction. He was also the one who successfully promoted it through his extremely popular lectures in Freiberg. Well, what was it he added to this mineralogical tradition? First of all, Werner made the time of formation of rocks, not their mineralogy, their most important feature. This would be one of his most important contributions. It was Werner who gave to geology the historical entities he called formations for rocks, formations that had been created at the same period. And we know how central that notion turned out to be in geology. Like his predecessors, Werner included a variety of information gathered about rocks, their height, slant, and so forth. Like them, he believed you had to get out into the field. You had to observe firsthand the rocks you were dealing with. But he was unlike his predecessors too, and it showed up when he came up with a classification for rocks. To the extent that his predecessors had classified rocks, they had relied on their mineral content. Werner's goal was to develop a systematic knowledge of all the data gathered about individual regions in order to determine when and how the rocks of the region had been laid down. From this, he would establish the classes of rocks that would make up his system. He came up with a new name for what he was doing. This is the name I promised earlier I'd tell you. I warned you then that it was not a name that would mean much to you, since it has not lasted. Werner called his new approach geognosy, based on the Greek word for abstract knowledge. Geognosy was the systematic study of minerals with a focus on close empirical observation and careful reasoning. By creating it, he was trying to emphasize the intellectual reasoning he felt was needed to put together the results of careful and widespread observation. I hope that you can see the difference in emphasis between his approach and that of the theorists of the earth we met in the last lecture. It's not that the theorists had no interest in empirical information. De Molay, after all, took as the starting point for his theory what he thought was an empirically demonstrable lowering of the seashore. The real difference is that the theorists of the earth were looking for one causal law by which to explain the history of the earth. Werner, on the other hand, wanted to put together a whole variety of empirical information. He was not looking for one causal law. He was looking to show how a lot of information fit together into a meaningful whole. He would use some of the names his predecessors had, but the way the whole system went together was his own. Now, using this approach, Werner did try to make sense of what must have occurred in the past. For example, he inferred that the oldest rocks, the ones that had formed first, sometimes deep in the Earth's surface, had originated from calm waters. Why calm? Well, because many of these oldest rocks were crystalline, like granite, for instance. That suggested to Werner that they had been consolidated in deep, still waters. These were the first ones to consolidate from the original gelatinous fluid that had once covered the entire Earth. Not all these first rocks were crystalline, suggesting that the waters had become less calm. Metals, too, had been among the earliest rocks to form. All these early successive individual formations Werner grouped together into what he called the primitive class of rocks. It included granite, gneiss, several forms of slate, on down to topaz and quartz. The oldest mountains, he thought, were made of primitive rocks. On top of the primitive class, often sloping against the flanks of mountains, came a small class of formations he called transition rocks, some of which had formed in turbulent waters. In fact, Werner argued that the ocean did not, as de Molay had it, gradually and continuously recede. Because of the position and the properties of the transition rocks, he inferred that the ocean had retreated and later advanced again, though not to its previous level. He was going by what he saw in the field. If certain rocks have certain properties and lie on top of certain others, then that is what must have happened. Transition rocks included less crystalline, more stony rocks. More recent than the transition rocks was the next class, the third class of formations. He called this class stratified rocks. Some of these had clearly resulted from mechanical pressure. Others, he thought, had consolidated by chemical means. Here were sandstone, coal, gypsum. These were the first ones to show any signs that organic life existed when they were laid down. How? They had fossils in them, of increasing complexity. Stratified rocks were predominantly low-lying and horizontally positioned. Some of them, he concluded from their properties, must have been consolidated in stormy seas, others in seas more calm. That brings us to the final class of formations. He called it the recent class. These came from two primary sources. First, there was eroded material deposited by moving water. The other source was the extruded material of volcanoes. Like most everyone, he thought volcanoes resulted from burning coal. But coal didn't occur below the stratified rocks of the third class. That meant that volcanic debris was relatively recent in origin. So that was the classification scheme he came up with. As I said, lots of students from all over Europe came to Freiberg to hear him expound it. And that included countries from across the English Channel, especially Scotland. And when he did expound it, it was always with an accompanying emphasis on the need to see the different classifications in nature, to make sure that what you found on excursions confirmed the arrangement that had been erected. Of course, Werner was confident that it would, since it was from field trips into the hills that he'd formed it in the first place. There's one thing about Werner's outlook that has been widely misrepresented, and I'd like to clear it up. Werner has been called a Neptunist because Neptune was the Roman god of the water and sea, and the sea played an extremely predominant role in his system. As far as I am aware, the term Neptunism, as I'll point out in Lecture 17, was applied to this kind of system by a Scotsman named John Playfair in 1802. Now, I can live with Werner being called a Neptunist. The sea is, after all, very important to him. But sometimes historians and others have made Werner into a so-called catastrophist as well. A catastrophist is someone who appeals to catastrophes, like floods, to explain things in nature. Catastrophes are sudden and dramatic, violent events that leave profound change in their wake. We'll meet some catastrophists in later lectures. My point here is that Werner was no catastrophist. Contrary to a widespread impression, Werner did not appeal to sudden and dramatic events to explain how the earth had developed. Werner held that the primeval ocean had eventually retreated over time, and that there was evidence to indicate that the retreat had occasionally reversed itself. But this had not happened quickly. A question that he must have been asked a lot was, where did all the water go? If you ask Werner that question, his answer was that he was aware of various speculations about it, but that he himself preferred not to engage in them. It was a bit like Newton's attitude when asked how gravitational attraction was able to be transmitted from the Earth to the Moon without an intervening medium to carry it. I make no hypotheses, Newton had said. That was, of course, a cover for saying, I really don't know. But it was also more than that. He was saying that he didn't think he should be proposing answers for which he had no evidence. Newton felt he had evidence that there was a force, however it got from the Earth to the Moon. How it did so, he couldn't explain. Werner's attitude was similar. He preferred, he said, not to endorse speculations about where the retreating water had gone. It was sufficiently clear to him that the waters had retreated, and that was enough. Speculating about the cause was relatively unimportant. We know that privately, Newton did wonder how gravitational force was transmitted, and that he did, in fact, propose a hypothesis in spite of his public statement. Again, Werner was something like Newton. He couldn't completely stay away from an idea about where the water had gone, at least late in his life. By then, it had become clear that water was composed of two gases, hydrogen and oxygen. Werner invoked that new knowledge to suggest the primal waters had decomposed when forming the atmosphere. What about the age of the Earth? We know that all of the theorists of the Earth had vastly extended the Earth's age. Buffon gave over 75,000 years, de Maillet into the billions, and Hutton said it was indefinitely old. How did Werner's estimate compare? First, I want to note that Werner joined those who were willing to extend the history of the Earth far beyond the 6,000 years that had been inferred from a literal reading of the Old Testament. Once again, he was uncomfortable speculating about matters that did not easily lend themselves to precise determination, but he did give a ballpark figure. The most he would concede was an oblique reference to a time when the waters, he said, perhaps 1 million years ago, completely covered the earth. Werner came from a devout, pietistic background, but he appears not to have allowed any traditional religious views he may have had determine his geological considerations. Still, I have the feeling that his attitude was quite different from the one we met in Desmoulins or in Buffon or in Laplace. He might have been closer to Hutton, for whom a personal deity seems to have been important. I have the feeling that Werner preferred not to talk about such things. He liked it best when he was lecturing on the meaning of things he'd observed, not on questions that didn't lend themselves to empirical verification. Be that as it may, the effect of Werner's work was to add another voice to those who argued that the earth was a cosmic body whose past had been shaped by natural processes. In the Germany of the latter half of the 18th century, this message was not shocking. I mentioned to you in Lecture 1 that the German states were experiencing a real cultural upsurge in the second half of the 18th century. Wissenschaft, systematic scholarship, was the operative word. Naturwissenschaft, natural science, was the application of systematic scholarship to the study of nature. And that was what Werner was trying to do with his new science of geognosy. He wanted to systematically correlate empirical data with sound, rational analysis. Werner's message, like that of the theorists of the earth in our last lecture, was focused on understanding the earth and its history as the result of natural process. But all of their views can be seen as a special case of the growing tendency to treat all aspects of nature to be governed by natural law. We saw it in the growth of Newtonian astronomy in Lecture 2, then again last time in the theories of the earth, and now again with Werner's geognosy. And we will continue to see it in the works of others here in the 18th century and on into the 19th century. Clearly, not everyone thinks this is a good idea. When the results natural philosophers depict suggest that the Bible has to be read with a certain degree of liberality, there are many who just cannot go along with that. They openly criticize the works of natural philosophers whose conclusions appear to challenge the Scriptures. In Werner's case, his views were greatly influential because of the enormous influence he exerted through his celebrated teaching at Freiberg. Werner helped to shape the attitudes that many thinkers of his day had. His students dominated the journals devoted to geology and mineralogy. Their notes started showing up in textbooks, much to Werner's annoyance, but it was not only the specific ideas. Werner's attitude about the need to stay close to the data of observation struck a lasting chord with many. Especially after the turn of the 19th century, there were those who preferred Werner's reluctance to speculate about grandiose ideas because they too preferred close empirical work. One scholar has referred to the Wernerian radiation to identify the enduring influence of Werner on more than one generation of geological thinkers. His influence lasted well into the third decade of the 19th century, an achievement that is not as appreciated as it should be. In the next lecture, we're going to change gears just a bit. We'll be talking not about the Earth as a cosmic body, but as the seat of various transformations of matter from one kind into another. We'll back up in time in order to pick up what was happening in the worlds of alchemy and chemistry. And there we'll see that a number of considerations will parallel what we've been investigating here. Namely, that the scope of natural law will be extended wherever possible to include natural processes and to take the place, in many cases, of God and his explanation of nature.